Welcome to another video on the electric drive, and in this video we are trying to find the relationship between the linear velocity of the piston and angular velocity of the crankshaft. So let us say we have a circular one rotating, just a minute, right, this one rotating circular crankshaft is there with key over here, and now if this rotate, let us say this is rotating, and you have got one mass over here like this, which is having a mass of m. Now this is supposed to move in the x-axis with a velocity v, and this shaft is rotating in the clockwise with the omega m. So this is a crankshaft which is rotating at a rotational speed is omega m radian per second, and this mass is tied up with this crankshaft, and the person over here, it sees that its linear velocity is, its translation velocity is v. So this tied up here with the rope. Let us say this rope is connected over here. Okay, and let us put a dotted line like this. Okay, so now at this particular point, if we find what is the speed tangential force over here is, this is the way tangential force we can find, and this tangential force is depending on the omega rotational speed. So that value, this velocity with which this is getting driven by here, this velocity will be equals to, let me not write v here, okay, this angular, this I will write here r into omega. This is what the tangential force at this particular point. Now to evaluate, to get a relation between this v and this r omega, we have got certain constants over here. One is, this is the beta. Another is, from this point to the center of this crankshaft, the angle is, let us say, alpha. Okay, so these are the two things, two different parameters that is available. So let me draw a line which is parallel to this x-axis in here. If I draw a line like this angle is nothing but alpha, okay, and this angle is the reflection from here, that is beta. Okay, so this is what we can get of here, trigonometric. So if I try to equate all the parameters towards this reference in this this reference axis, what I will find, this velocity, if I try to get its component over here, this will be v cos of beta, and r omega, its component over here, this angle is how much? This angle is nothing but 90 minus alpha plus beta. So here you have r omega cos of 90 minus alpha plus beta. So this comes out to be, the velocity can be given as r omega sine, in the cos of 90 minus this is sine of alpha plus beta divided by cos of beta. So that is how we have a relation of the translational velocity of the piston having a mass m in this direction, positive x direction, and with the rotational velocity of the crankshaft. So okay, we get the relation like this. Now what is the load torque we can find? Okay, and before that, since this shaft is tied up with the motor, right, the shaft is tied up with the motor, that's on the background, right, with motor. So if this motor is rotating, so this is crankshaft, this is rotating, and that will try to pull this piston. So from 0 degrees to 180 degree or like this, it is moving forward. Then from here to here again it will move backward. Like that it will make a to and fro motion. What is the inertia of this mass referred to the crankshaft? What referred to the motor? We can find if we just use the kinetic energy, that is J is equal to half J omega m square is equal to half mv square. So we can write this in this way. And if we substitute the value of V here, then we can get what is the J equivalent of the mass, that is M. Instead of V, we will put the value R omega sine alpha plus beta by cos of beta. Since this is a V square, we will make it square everywhere. Yes. And divided by omega square, this omega square cancel up. So we have got a mass M multiply with R square sine square alpha plus beta whole divided by cos square beta. So this is what the J equivalent of this piston refer to the motor crankshaft, right? So here by this we can get the value of J equivalent. Now what is the dynamic power required by the crankshaft? Let me write dynamic power. So we can write P dynamic is equal to rate of change of the kinetic energy, right? So the kinetic energy can be given as half J omega square. J we have calculated J equivalent, so let us write here J instead of J equivalent always. So we can write here this is d by dt of half J omega square, which is equal to half J 2 omega d omega by dt plus keep this omega square dj by dt, like that. And what is P dynamic? P dynamic we can write in terms of let us cut this half off. P dynamic is power is equal to omega m speed angular speed into torque. What is the total torque? We can write total torque is motor torque minus the load torque, right? So this 2 equals to, this side will be J omega d omega by dt plus omega square by 2. This dj by dt we can write dj by d alpha and d alpha by dt. If we write like this, what is the purpose of writing here? Because this inertia, when this alpha, this point is here at the 180 degree, then it is moving up, so the effect of this mass get changed. The inertia will definitely get changing because of the position of this alpha. So that is why we segregate this in terms of dj by alpha into d alpha by dt. So if we write down this entire equation and cut down this omega m, this is omega m, the motor speed. So all these things. So we get here total Tm minus TL is equal to J d omega m by, this is all omega m motor torque, right? Motor speed in radian per seconds. D omega m by dt plus omega m by 2. What is d alpha by dt? D alpha by dt is rate of change of angle, that is also omega m. So we can write here omega m square, because this term is nothing but omega m. So omega m square by 2 into dj by d alpha. So in this way we get what is the motor torque and what is the load torque required for this. We can calculate in this one. So what else is left here is the load torque also, because load torque also we can write down here. The TL is of the piston is force into velocity divided by efficiency, right? and this into omega, so omega will also be here. So this is what the load torque is. This, when we calculate the value of the load torque, then we need to remember that if it is directly connected to this mass is connected to the crankshaft, then its velocity is depending on the crankshaft rotational velocity also. So that's why it is divided by omega m. So here instead of V, we can put the value of V, that is R omega sine alpha plus beta by cos beta. This omega m will cancel out. What remains is F into R sine of alpha plus beta by cos of beta. So in this way we get the value of TL also. What is the load torque reflected to the crankshaft? So once we know the value of TL, we put the value of TL over here. J is known, d omega by dt we can calculate, and omega square by 2 dj by d alpha. So all these things if we can get what is the finally what is the electromagnetic torque, or what is the motor torque required by the motor. So there are terms like Tm, there is another term called Te, electromagnetic torque Te. So we will discuss all these things later in another video. But for now you can write here this motor torque as Tm, or if you write Te also, please mention it is the motor torque, mechanical torque that is developed or that is required by the motor. So thank you very much for patiently listening to the video. We will have next video, we'll have more concepts on electric drive. Thank you.